share his slides and take over.
Thank you. So good morning or good afternoon, wherever you are. So this is going to be actually a very gentle introduction into an exciting computer game, which is called Formalization of Combinatorics on Words in Isabelle, HOL. It's a joint work with Štěpán Starosta and a couple of students, a bunch of students. So actually, the main part of my talk, I have just one slide. So main part of the talk will be examples to give you really an impression of what it means to make the formalization for complete beginners. Right? So this is the user interface, and it has two main windows. You can see. So the upper window is the place where I write my formalization, and in real time, there's a background process which is evaluating what I have written and giving me feedback. So Isabelle tells me what she thinks about what I have written. So, for example, if I write lemma A equals B, such a stupid lemma, so I am immediately in real time informed that this is not true. In general, this is not true. And because it may happen, right, that A is different from B. So this is the first example of an automation. Right? But let's look at a more reasonable example. So I have here an example of a very trivial claim. And actually the main purpose of this example is to show you how the proof looks like. And I would like to convince you that actually the proofs you get with Isabelle are humanly readable, that you can really consider them as real proofs. So I assume that I have a word which is composed by P and P times S, and I want to show that the prefix is at most of the length of the word, right? So I start the proof, and I first observe that P and S is of the same length as W, right? So this is a trivial claim, which is introduced by have as a keyword. And of course, this is kind of trivial, but the general pattern of proving such a step would be that you give some auxiliary fact that you want to use, which is our assumption in this case. And then I invoke, and this is important, I invoke some kind of automated checker, right? So I'm not going down to axioms of the logic, but I stop at some moment and I will ask Isabelle whether she would accept this as one step. So this is one of these procedures, which is called simplification. And you can see that actually everything this simplification does is that you can substitute here PS, replace it by W, and then use the reflexivity of equality or something like that, right? So this is something which is hidden. We don't want to go deeper, even if we could, right? But I want to stop here with splitting the proof. Well, then we use this property. It's kind of non-trivial property, but actually trivial, humanly trivial, that the length is additive, right? So I want to point out this step, that actually the length of PS is the length of P plus length of S. And using the previous fact, and again, I'm using some slightly more advanced method, and it is accepted again, And finally, I show, there's a different keyword because this is I am showing what I was supposed to show. I show that the fact that what I was supposed to show is true, using the fact, using the previous fact. So using the fact that kind of, again, the addition is monotone. So if I add something, it will be bigger. And here I use again some simple checker, which is called linearit, which suggests that it is the method which is able to check basic arithmetic facts. And I write QED, and if everything went well, which went in this case, I am informed that I have my theorem example 1. I can call it lemma or theorem, but eventually Isabelle calls everything theorem. So this theorem, which is called example 1, and it is this one. You can see that it was transformed from this assumes shows to a form of implication. So again, this is an inner form of maybe a bit less readable, but quite obvious. I don't speak about these question marks. They are a bit ugly, but don't care about them. So
may I ask a quick question?
Yeah.
Where do you say what the domain of the objects that you're working with?
Very good. Yeah, very good. I could say it implicitly. I could say it explicitly. Like this, that it's a list, but I don't have, thanks to a so-called type inference, which is inferred from these brackets. So these brackets are defined for lists, so I don't have to be explicit. But this is a very good question. Otherwise, I would be informed that the type is unclear. So here the type is inferred from the functions, which is in most cases, this is quite convenient. Yes. Okay, so my point was that you can choose how big steps you want to see, right? So for example, now after example 1 is proved, I can use example 2, which is actually the same thing for a special case of W, right? And what's nice is that as soon as I write this lemma, again, in real time, Isabelle informs me that this is actually already proved. Namely, she says this can be solved directly using your example 1, which is very handy. This is one of the advantages of Isabelle, I would say, again, over other provers, which don't have this kind of automation where you have to search for existing proofs, for example, by text search or something like that. Right, so I can write now that using the assumption and using example 1 by BLAST. BLAST is a very simple method which just combines facts. So actually you can see that the whole game is modular. You are building your lemmas, and then you can use your lemmas as a basic steps, of course. That's what makes it eventually powerful. Even if you start from very modest axioms, eventually you can build a powerful theory. Well, the typical skeptical question, or I would say beginner skeptical question, is what if I don't trust these methods and I want to see the proof? So typical answer to this question is that you shouldn't care, but it doesn't sound very honest. So in this case, I gave you, I want to show you an example of what the real proof is. Right? So this is the proof of the example 1, broken to axioms. So actually why I'm showing this is like to convince you that this is something you actually don't want to see. Because what do you do when you get such thing? Well, you write a computer program that will check it. And that's exactly what Isabelle does. Right? So you don't want to see this. You are just trusting that actually everything is eventually kind of converted in such a proof, which is really then checked by natural reasoning, modus ponens, and so on. Okay, so another example. Let's look at this slightly advanced claim that if a word is primitive, then its conjugate is also primitive. So actually, I want to prove it, and I may be kind of surprised that it is not there yet. I'm not informed that it's already proved. So now, what can you do? And this is the biggest fun, actually. Is something which is called sledgehammer. So there is a sledgehammer, which is a collection of outside automatic provers. You know, this is formalization. This is not automatic proving, but it is integrated. You have a bunch of provers, and you can pass it to them, or Isabelle can pass it to them. So I can apply the sledgehammer, you know, and this is biggest joy of the formalization when you see this proof found. And then you can just choose which one you want. This is the simplest one, but I want to show you this one. Right. So the Isabelle tells me, actually, this can be proved using prim rotate conv and rotate append. And then you can click on this prim rotate conv. And you can see that actually my theorem or my lemma was there almost, but it's actually in a stronger form. It is an equivalence, right? So the problem is that I was not informed automatically that it is already proved because it is slightly different, but I can ask the sledgehammer to find, you know, if it is so close to something, then the sledgehammer will find it. So it is actually this prim rotate, it is the equivalence. And actually, but if you look here, here is a rotate, you know, here's a rotate. So you need another component for the proof, namely what's the relationship between rotation and appending, right? So this is this lemma, you know, I'm clicking, if you click on it, you will get to the place where the lemma is. So here it is explained that the rotation by some length is actually conjugation, right? And also I think this is very nice that, you know, the sledgehammer will show you such simple steps, right? You don't have to search through the libraries whether there is something like that. You could do that. You could search for the word primitive or for the word, I don't know which one, rotate maybe. But sledgehammer will tell you, you know, these two theorems are already there, and together they can give you the proof. Actually, there is another one. There is prim conjug, which is another one, right? So there can be more of them. This is actually the other two were already in the main library. This is our lemma. Right? So this is like next message I wanted to give you is that there is this sledgehammer. Well, and then now finally, this is, let's say, end of primitive examples, and I want to show you now something that we did, right? So sample that, just two examples of what we did, slightly more advanced facts. So one theorem, for example, still fairly simple, is that if two words do not commute, then they form a code. You know, and I'm not showing you a proof because this is just, you know, this is already, again, you know, it's this is already there. I'm showing you something which is there, and it is then the theory graph lemma. So actually, it's a consequence of a graph lemma. So we have a theory where the graph lemma is proved, and this is a consequence of a graph lemma. You may want to know how code is defined. Right? So you can click here and you can see how the code is defined. Right? If you have two sequences and the concatenation is the same, then the sequences are the same. Right? So this is the definition of a code. Another example, probably most famous, periodicity dilemma. Right? So if a word W has a period P and a period Q with a notoriously known bound, then it has also a period GCD-PQ. And again, it's proved somewhere, actually in the theory called, surprisingly, periodicity dilemma. And the proof is reasonably long. It's not very long, actually. Well, this is not very long because there's something preceding, so this is not the whole proof. Okay. Actually, we have there even the construction of this fine envelope word, which shows that the bound is optimal. So that is the verified construction actually of the optimal fine envelope word. Okay, so far so much the examples. So actually now the unique slide I have. So why we are doing this, or what we actually do, right? So this is a part of a project that we have, ongoing project, and so our plan is what I have shown you. We want to formalize foundations, and we have the basic auxiliary file has about 500 lemmas at the moment. Then we would like, or we almost have a textbook that would be like a verified lecture notes of a basic course in combinatorics on words. Well, I should say that in our case, combinatorics on words means combinatorics of finite words. We have nothing about infinite words. So this awaits somebody else maybe, or that may in some future we may move to infinite words, but at the moment we are working with finite words. Well, and now the item 3 is kind of why we are doing that. That's the motivation that we would like to formalize, and we already partly did this, to formalize existing hardly readable or checkable proofs. Well, so the idea is, I think that you would agree that in our field, it's often a pain, to write proofs. And especially to review them, for example, or to be a referee of a technical paper. And usually when you start to read the proof, you find some gaps, right? Empty words was not cared for, or a small step was missed, and usually it can be easily fixed, and the author would say, okay, you must understand that I meant this and not that. So if you just write it down in Isabelle, then you can, we can get rid of all this labor. And you just can focus on ideas, and the hard work is done by the computer, which is, I think, why we have computers. And then maybe the big hope, or the big idea, is that eventually, if your building becomes big enough, then you can actually maybe start to attack some open problems which are maybe just too complicated. I think that maybe this is also your experience, that some problems are just beyond human reach, because simply it's simply too complicated. And as soon as you have all these auxiliary lemmas, and the power of the computer, which can combine, all 2 million of them, in seconds, then maybe you can proceed towards new results. Okay, so actually the only thing you have to remember from this talk is this address of the GitLab repository, which features this avatar, which I want to thank Srečko Koberlek that he allowed us to use this poster, which was painted by Michel Mende-France for 2005 Combinatorics on Words in Montreal. So this is this repository, and we would like really to invite you to try if you are interested. So there is quite, we try to make a comprehensive README here, so you can learn here how to install Isabelle, which is actually takes 5 minutes. And actually it's Isabelle 21, which was released. Actually, it was released yesterday. So it's a brand new release of this year. Every year there's a new release with small changes. And there are some, helps how to work with that. And then there is an overview of what we have done already. So maybe I would briefly run through that. So this is the basic file, which is CoBasic, which contains these, let's say, 500 auxiliary claims. Then there is a similarly things like conjugation, root, primitive root, and so things like that. Prefixes, suffixes, left factors, and things like that. Then there is the file submonoids, which contains the HOL, also submonoid, basis, code, and free HOL. The definition of code was I have shown you was from this theory. Then there is the periodicity dilemma. I told you we have Linden-Schützenberger. It's a little theory where Linden-Schützenberger theorem is proved. We are working on the rests now, because this is for me, it's a prominent example of a result which you have heard maybe myself talking about it several times, that this is a proof. This is a very important proof which was just forgotten, because maybe because it's too complicated. I don't know. Graph lemma, very nice. You can check what kind of graph lemma we have. There's something about borders and Linden words with an addition, and then a more technical stuff it's overlaps, factor interpretation. This is kind of preparation for LRS and things like that. Speaking about these old proofs and their formalization, we already have in print or submitted and accepted the formalization of Juhani Karhumakis' result about the intersection of binary words. This is the proof, let's say simplified or modified proof, that I presented 2 years ago at Laboro. So for the publication we have formalized it. So now it is not only, let's say, reproved, but it's even checked and formalized. Okay, so I think that's all. More or less, I could go on, but maybe I will make.
Okay.
Be interested in talks in questions.
I see a question from Gabriele Fici.
Ciao Stefano. How are you
Ciao, come stai?
Nice talk. Thank you. I have a question about introduction of new definitions in.
Yes.
So how can you showed us some theorems. So
yeah, I showed you even some definition, So for example, code.
Yeah, this is a definition of code.
Okay, code. But okay, so let's look at some definition. Primitive, right? What primitive is? Definition, right?
Yeah. I'm interested in adding new definitions. For example, I don't know, a billion square. How is it done?
Well, you have to figure out, right? So, for example, for a primitive word, this is just a simple formula. For abelian square, you would need something like a concept of multiset. So the work is that you have to guess that you are not the first one who is interested in multisets. So you can search in the library for the term multiset, and then you will say that abelian square is a word of the form U times V, where multiset of U equals multiset of V. Okay, so you can use other data structures that you can use anything you have. So not only lists, but also you can use anything you have. And, okay. Yes. Yeah. For example, this is a power, right? This is defined by us. So the power for lists is a special case of powers. Actually, okay, maybe this is too complicated. But for example, power, you can see that there is a strange kind of power. So this is a special case of the monoid. So the words are monoid, and there is a power of monoids, and we are using the monoids have a power, but we give it a new notation. For example. So usually the basic like bricks, basic elements are available already. We just put them together.
Okay, I see a question from Florin Mania, please.
Yeah, hi Štěpán. It was a really nice talk. I enjoyed it very much. I have some, maybe it's naive question or kind of maybe not so interesting.
Questions are the best.
So in your sledgehammer here, you have these SMT solvers, the CVC4, Z3, and
Yes.
I don't remember the others. Can you like use any SMT solver of your choice there?
I am not expert in this. I not easily. I know that in probably not. You know, I mean, you can do anything you wish. So actually, this is the whole code. The basic language is ML. It is written in ML language. So you can actually program whatever you wish. Whatever you can prove in write in ML, you can write down. But this would be a large development, I think, which you can start. You can do to add a new prover. You know, because what's difficult is of course the communication. You have to write the interface between the, you know. So that's a huge work. In 2021, there is a new prover which I don't know, which is not here yet. I don't have it yet here, but there is another prover which was added in this year, for example.
So I mean, I know that CVC4 and Z3 are particularly unfriendly to the user when you want to ask them to prove something for you, but they are also very fast and very efficient. So they are very nice.
So this is perfect. This is because Isabelle communicates with them for you.
Yeah, that's great. I also, so maybe this is the naive part, but maybe you said that you didn't look too much into that. I know that both CVC4 and Z3 have a very important string solving component, which basically from our point of view is a solver for word equations. And is there any way to maybe exploit this? Like the fact that they are also, you know, dealing with words, and in the case when they solve a word equation, they basically provide you with a description of one or multiple solutions.
I think, well, at least for me, I am approaching Sledgehammer completely as a user.
So exactly like a sledgehammer.
As a sledgehammer, yeah. But as far as you know, I follow some discussions. There is a great user list, you know. So if you subscribe to the list, then you will learn a lot of things every day. So from the discussion that I could follow is that you cannot really tamper with the prover, you know. You
okay.
have, yeah.
So they use it sort of like a black box. They just
it is very much a black box. Yes.
Okay, thanks.
Okay, I guess that's about all the time we have. So thank you very much, Štěpán, for
Thank
your
you.
talk.
Thank you. And try to use it.